What's up? It's time to review some concepts in projectile motion. Let's go! So firstly, what even is a projectile? A projectile is any object with an initial velocity following a trajectory subject to gravity and air resistance. However, for our purposes, we will actually ignore air resistance since it can be quite complicated to model. In describing the initial velocity that will define the path taken, we need two parameters, v0, the launch speed, and α0, the launch angle. The second key concept we need to apply is the independence of motion along x and y. This just says that the motion along each axis can be considered separately. Since we assume that only the downward force of gravity is acting on the projectile, we must have that ax is equal to 0 and ay equals -g. We can see this more clearly by looking at this diagram. Along x, there is no force, so the particle does not accelerate along that direction, instead traveling uniformly. However, along y, gravity accelerates the particle, increasing its speed. When we superimpose these motions, we get the path of a projectile. Now, let's discuss the key equations. First up, initial velocity. To analyze the motions along each direction separately, we need to find the velocities along each axis. So if we have an object with initial velocity shown below, how would we get the initial velocity along x and y? Trigonometry. Doing that, we should get that v0x is equal to v0 cosine α0 and v0y is equal to v0 sine α0. Note that since v0 and α0 are constants, these values are constants too. Now, how about the velocity at any point in the particle's path? Velocity is no longer constant over time, so we now need to recall the kinematic equation, v equals v0 plus at. We use this to resolve the velocity into its components. If we use the fact that ax equals 0 and ay equals -g, we get that vx is equal to v0x and vy is equal to v0y minus gt. We can substitute our expressions for v0x and v0y from earlier and we obtain vx is equal to v0x is equal to v0 cosine α0 and vy is equal to v0 sine α0 minus gt. Now that we have our velocities, we can begin to consider displacement. Again, recall the kinematic equation, x equals x0 plus v0t plus 1/2 at squared. We resolve into components, keeping in mind our expressions for ax, ay, v0x, and v0y. Doing this, we obtain x equals x0 plus v0 cosine α0 t and y equals y0 plus v0 sine α0 t minus 1/2 gt squared. We note here that the second formula is particularly useful for finding the time at which a particle hits a certain height. Oftentimes, this amounts to an application of the quadratic formula to solve for t. Now, suppose we had expressions for component velocities along x and y. What often matters to us is the actual velocity vector itself, which includes its speed and direction. For speed, we simply apply the Pythagorean theorem to get v equals square root of vx squared plus vy squared, and for direction, we apply trigonometry to get alpha equals arctan vy over vx. Note that these formulas apply at any point in the particle's trajectory. Speaking of, what if we want to trace the trajectory of a particle? If you look at this diagram, we see that it looks like a parabola. But how do we know that the path is a parabola? It's simple. Just look at the equations. For displacement, we know that our equations are given by these. X is a function of t, and y is a function of t squared. Intuitively, this gives us a parabola. But if we want to be more explicit, we can also eliminate t to get an expression only in terms of x and y. For simplicity, we set x0 equals y0 equals 0. This amounts to setting our launch point at the origin. We solve for t in the x equation and plug it into the y equation. And if you do the math carefully, we should get that our final equation is given by y equals tan α0 x minus 1/2 g over v0 cosine α0 quantity squared x squared. Indeed, this is a parabola. Now that we have those out of the way, what do you say we discuss some special equations? So, if you got all those, we are actually capable of solving almost any projectile motion problem using those equations. However, if we want to analyze a system purely in terms of positions and velocities, we need to eliminate time. That is, we want to get time-independent equations. Don't worry, there are just 4, the first of which is the time to max height. Here, we need to leverage the insight that at maximum height, the vertical component of velocity is 0. Indeed, this is what we see in the diagram at the top of the parabola. So, this tells us that we need to use our equation for Vy, setting it equal to 0 and solving for t. This gives us that t equals v naught sine alpha naught over g. Now, what if we want the time of flight? The formula we're about to discuss requires a special assumption that the launch height equals the landing height. If we assume that, we can leverage symmetry and simply double the time to max height. Alternatively, we can use this equation again, then set Vy equals negative V naught sine alpha naught. This amounts to negating the vertical velocity, which follows from the symmetry at equal heights and the uniform change in velocity. If we perform those calculations, we then get that capital T is equal to 2T is equal to 2V naught sine alpha naught over G. For the maximum height, we define this as the height when T equals the time to maximum height. So, bringing up our equations for t and y, we simply combine these two and eliminate t. Note that we set y naught equals 0 for simplicity. Doing that, we get that the maximum height h equals v naught sine alpha naught quantity squared all over 2g. Next up, range. Again, we require the assumption that the launch height equals the landing height. Then, the range becomes the horizontal distance traveled during the time of flight. Pulling up our equations for capital T and x, we simply repeat our process from earlier. We substitute capital T instead of t in the x equation, then eliminate it. Again, we set x naught equals 0 for simplicity. This gives us that r equals v naught squared sine 2 alpha naught all over g, where we have invoked the double angle identity for sine. And that's all. We have all the formulas that we could need to solve a problem in projectile motion, so let's try a practice problem. I call this problem Clear the Bases. Let's read it out. A batter hits a baseball from the ground at 37.0 meters per second with an angle of 53.1 degrees. What is the equation of its trajectory? What is its position and velocity at 2 seconds? What is its time to max height, time of flight, maximum height, and range? What is its final velocity? This is the diagram for our problem, and note that we assume x naught equals y naught equals 0. I encourage you to pause the video and try this for yourself. I will leave a pause of about 5 seconds before discussing the solution. And time's up. So, to solve this problem, we first list our given. V naught equals 37 meters per second, alpha naught equals 53.1 degrees, and t equals 2 seconds. To get the trajectory, we use our equation from before and simply substitute our given. Performing the calculation gives us y equals 1.33x minus 0.01x squared, which in turn gives us this plot. Now, how about our position and velocity at t equals 2 seconds? Here, we apply the time-dependent equations. We first pull up the ones for position and remember our assumption that x naught equals y naught equals 0. Performing the calculations, we obtain that x equals 44.43 meters and y equals 39.58 meters. For velocity, we repeat our process. We get the time-dependent equations for velocity and substitute t equals 2 seconds. Performing the calculations, we get Vx equals 22.22 meters per second and Vy equals 9.99 meters per second. But we're not done. We only have the components, so we need to get the magnitude and direction of the actual velocity. Performing the calculations, we get that V equals 24.36 meters per second and alpha equals 24.21 degrees. We summarize our answer here. Next up, time to max height and time of flight. We simply bring up our equations from before, and performing the calculations yet again, we obtain that t equals 3.02 seconds and capital T equals 6.04 seconds. For the maximum height and range, our equations are given by these. Substituting, we get that h equals 44.67 meters and r equals 134.15 meters. If we look at our plot, we'll see that these indeed are the answers. Lastly, for the final velocity, we note two things. Since Vx is constant, the final horizontal velocity must be the same as it was initially and at t equals 2 seconds. Vx equals 22.22 meters per second. Meanwhile, for the final vertical velocity, we again use a time-dependent equation. Note that we have used capital T to find the velocity after the time of flight has elapsed. This gives Vy equals negative 29.58 meters per second. Performing the calculations to get the magnitude and direction, we get the final velocity of v equals 37 meters per second at alpha equals negative 53.1 degrees. Curiously, this is just the initial velocity reflected across the x-axis. Again, this should make sense because of the symmetries in our problem. And with that, thank you so much for watching and see you next time.